Hey everyone, how's it going? Thanks for making it today, even though I couldn't be there. My name is Ryan Lefebvre, and I'm going to run you through my project real quickly. So, I mainly looked at stress-strain relationships. I also looked at strain reversals, but for the purpose of this presentation, we will just be touching on the stress-strain relationships. So, I started out with some research, and what I kept getting pointed to is this Ramberg-Osgood equation. You can see it on the right there. It's equation 1. It basically solves for strain given stress, elastic modulus, the tensile yield strength of your material, and the strain hardening exponent that we will look into in the next slide. And this equation is basically used to get a more realistic description of your stress-strain curve, including strain hardening, and it just captures what's going on in the plastic region. So in order to solve for the Ramberg-Osgood equation, we first have to solve for our strain hardening exponent, which is unique for every material. For this project, I decided to use A992 steel, so we will be running through it with those numbers. To get N, you have to find 2 points within the plastic region. I chose to go with the ultimate point and the yield point because those are the most available values. Substituting for equation 2, we get equation 3, and if we put 65 ksi in for our ultimate strength, 50 ksi in for our yield strength, and 18% for fracture strain and 0.2% for our yield strain, we get a strain hardening exponent of 0.056. So if we plot the Ramberg-Osgood equation against the linear equation that we've been using in our assignments, we notice some observations right off the top. So the RO curve softens before the linear curve, and it also slowly continues to gain strength after yielding. So how does this affect our pushover model? Some things we can expect are that the RO model will displace more initially, but as it gains strength, it may creep up and eventually get to a higher force per displacement than the linear model. The model I used for this project is a simple one. I wanted to create a model that was driven by tensile deformation and one that would show at least 2 members reaching yield in a pushover analysis, so we can see what's actually happening. So when looking at the results of our pushover analysis for linear versus Ramberg-Osgood model, we can see a couple things. So as we expected, the RO model displaces more initially, but eventually gains strength and passes the linear model. But we also see that these differences are fairly insignificant, and it should be noted that the linear model is computationally much more efficient. So in practice, if you're doing a large model, it might make more sense to go with the linear model. So for my project, I also wanted to look into how ETABS handles its nonlinear stress-strain curve. If you go deep into material settings and under A992 steel, you can actually take these points right out of ETABS and plot them. Comparing them to the linear and Ramberg-Osgood model, we can note that the ETABS is similar to the linear model in that it's linear until yield, but also similar to the RO model in that it includes strain hardening, but in a more linear fashion. Taking a look at the pushover analysis results from ETABS, we can see that compared to the linear and RO model, it seems that the ETABS model is yielding after Fy, which is kind of strange. And also, because the ETABS model doesn't account for softening around yield, but does include strain hardening effects, it leads to a pretty unconservative model. I wanted to do a little bit of exploring to see why ETABS was yielding after what would seem to be 50 ksi. So I created a few different equations, and you can see the linear modified equation here is the one I ended up going with to try to match the pushover analysis from ETABS. Instead of doing full yield at 50 ksi, I took the average of the yield and ultimate stress. When running my linear modified equation, we can see that it closely follows the ETABS pushover results pretty well. You can see the purple line is the ETABS pushover and the yellow line is the linear modified, and they're almost right on top of each other. And it's pretty interesting that I was able to capture this with a far simpler stress-strain relationship. In conclusion, we have many options, and we're not limited to just the Ramberg-Osgood equation. There's many more based on other research. But from what I worked on, we can see that the Ramberg-Osgood equation, which is supposed to be the most correct equation, is actually the most conservative. And ETABS ends up being the least conservative, which I found to be pretty interesting because that's a commercial structural software that we use to actually analyze and build buildings. But fortunately, we primarily work within the elastic range, so hopefully it hasn't caused any damage. All right, that's it. Thanks for listening, guys.